All right, how's it going? So, questions? So, I'm getting emails from people about PA4, and let me mention a few things that I'm seeing or hearing from students. So suppose your input is something like, this is a test, hello, this is a test, hello, hello. All right, so there's a sample input file, and this has two phrases in it. This is a test and hello, and your final output should be 3 times we saw hello, and 2 times we saw this is a test. Okay, first general comment, right? Do not try to read your entire input into memory before you start processing, okay? That will blow up on War and Peace, and it also makes your program harder to write, right? It works best if you process your input as you're reading it in, right? So this is a test period. Okay, I've just seen a phrase, and I've been saving what I was reading into an array, so now my array contains this is a test, null terminated, add it to your dictionary. Never seen it, I'll put it in my dictionary once. Hello period, there's my next phrase, hello, right? This is a test, there's a phrase I saw before, there's hello, I saw it a second time, there's hello a third time, and I'm done. I could have 1,000,000 lines in my input file and your program should still work, right? And if you try to read all of your input until the end of the file and save it in memory, you're gonna run out of memory, right? But you don't need to do that. You only need to read at most 201 characters at a time. And if the phrase is longer than that, just keep reading and ignoring, right? Don't save till you get to the end of a phrase. And now you got a string of up to 200 characters, and you need to add that to your dictionary. You need to make a new entry or bump up a count, right? And it doesn't matter if that's one of 1,000,000 lines of input because you're processing it as you go. Related to that is this idea that if you use fgets, right, fgets is going to give you back all of this. And that's not a full phrase yet. You're going to need to somehow remember that we saw the start of a phrase. Maybe there's a period here which will end a phrase, maybe not. So I'll have to call fgets again and read this. And I'll have to call fgets a third time and read all of this. And know that this is part of the previous phrase and put this together with this and this to come up with my first phrase. Do whatever processing I need. And then at the end of the processing, instead of going back and calling fgets, start from the middle of this string that I already read and keep reading and get to the end of my phrase and deal with that. And then instead of calling fgets again, continue at this point of what I got from fgets, get to the end, realize it's not a phrase, call fgets at that point, right? And this is really confusing to try to do. You can make it work, right? But there's a whole lot more ways to not get it to work than to get it to work, right? Now if you read one character at a time, there's a T, that's the start of a phrase, start, phrase, phrase. There's a new line that's part of a phrase, there's a new line that's part of a phrase, T, ST, there's a period, that's the end of the phrase. And as I was reading these, I was copying them into an array starting at character 0. Now my array contains this is a test, right? And I go ahead and I do whatever I have to do to add that to my dictionary. And when I'm done, I just start reading characters again. Read a character, that's a space, so it's not the start of a phrase yet. There's an H, that's the start of my phrase. And now I keep reading a character at a time until I get to the end of a phrase, and I save everything that I read. Now I've got this sitting in an array, and I do exactly the same thing. See if it's in my dictionary. If it is, bump the count. If not, add it, set the count to 1, and you keep going, right? So this is why I'm suggesting you read a character at a time, which is why you want to use getChar, right? And if you do your own version of getChar, it's already taken care of making things uppercase, changing new lines to spaces, ignoring parentheses and things like that, right? So it's modularization. It's breaking things into pieces, so you don't have to do everything inside one big function, right? You can do that, but it's really, really tricky. And most of the code that people are showing me that they're having trouble getting it to work, it's because they're trying to do a lot of things inside one function, possibly everything inside one function, right? And your goal in modularization is really to sort of minimize what you have to do in each function. So this function, all I got to do is read a character, make it uppercase, make sure it's not a parentheses or a weird character, and make sure the only white space I will return is a single space, right? And that's a nice, succinct description of a function, right? And if you make that and you call it, my get car, right? You're done with that. Now I need to read from input using my get car until I find the start of a phrase. So read a character if it's a space or a punctuation, read another character if it's a space or a punctuation, read another character, that's just a while loop. When you read a character and it's not a space or a punctuation, you found the start of a phrase, and your function is done. Right? So it's these smaller functions that you're going to put together. And part of the challenge of programming is figuring out what those functions should be and how they should work with one another. Right? And this is where the idea of working out an algorithm comes in. Right? Before you ever write integer main, before you ever write integer I equals 0, you should have an algorithm. Okay? This is like doing a schematic in 250 before you start building the circuit. Right? Don't even touch your proto board until you have a schematic. Why? Because the schematic is where all the hard work comes in. This has to go to pin 1, and this has to go to ground, and this has to go through a resistor, and it has to connect to this pin and that pin, right? And you figure that out on paper instead of on the proto board where you can put things in the wrong hole or run out of space or things like that. You figure it out on paper, and then from the paper schematic, you build the circuit, right? From the algorithm, you write the code. And then, when you run the code, if it doesn't work, you can debug it. So you build a circuit and it doesn't do what it's supposed to do. What's your next step? You go to your schematic and you look at the circuit and you compare. And there's ways that you can start from the output, set up some inputs, take voltage readings, see where they're coming from, and sort of work your way backwards, right? If you've done 250 with me, we've gone through this. Same thing in here. Here's my program. I compiled it with a -G switch. I'm running it in GDB. Here's my algorithm. Okay, algorithm says first thing I should do is input one of my characters that I care about. Well, the first thing my program is about to do is call my get car. Okay, go ahead and say next and see what the return value is and make sure it's a character you care about. If it's not, you found your bug. Something wrong in my get car. If you got that character, okay, the algorithm says I should store that in my output string. Go ahead and step through your code until it stores in the output string. Now look at your output string. Did it store it? No, it stored it in position 5 instead of position 0. You found your bug. Right? And at some point, there'll be some discrepancy between what your code is actually doing and what your algorithm says it should do. Right? If there's no discrepancy all the way to the end, your program must be working or your algorithm is incorrect. So you have the algorithm, work out the details there, make sure you understand it, and then write the code. And then if the code's not working, step through, compare it to the algorithm until you find a bug. Once you find a bug, go back to your code, figure out where the bug is, fix it, recompile, go back to the beginning. Start from the beginning, run it in GDB, compare to your algorithm, right? So this is how you debug. It's a systematic way to debug. Now there's other ways. You can stare at your code and cross your eyes and hope that you see a pigeon and the pigeon tells you where the error is. That works sometimes, okay? Or you can just keep changing things at random until it seems to work, right? Sometimes that works. But ideally, when you finish your program, you should have absolute confidence that it works and that you understand exactly what it does, right? Now that doesn't always happen. Sometimes you just kind of you get it to work and time's up and you submit it, right? And you hope. But ideally, there should be no mystery in the end, right? If you believe your algorithm and you coded that into C, right, your program should do what your algorithm says, and it should not be a surprise or a mystery if it works, right? So that's kind of the goal. And it comes from starting with a clean algorithm. either on paper or in your head. And at some point, you know, people can build circuits without schematics because they look at a circuit and they see a schematic in their head. Same thing with code. At some point, you look at a bunch of C code and you see an algorithm, right? And if you're at that point, or when you're at that point, right, that's great. But if you're not there yet, right, you got to explicitly write an algorithm first. And it helps you get to that point where you look at C code and you actually see algorithms in your head, and then you're just more efficient. So does that make any sense? Yeah.
What's the bubble sort, the occurrences, right?
Say again?
In the PA, what was the bubble sort?
You're supposed to sort somehow. Bubble sort's probably the easiest, but if you have some other sort, you can use that. But don't call the system sort.
Okay.
All right, code it yourself. But bubble sort's probably familiar to most people.
Would there be any reason for GDB to execute a function differently than just running it?
Yeah. So if you have memory issues, if you have an array going out of bounds or something like that, or something that's not initialized, sometimes compiling with GDB will give you different results. Unfortunately, sometimes it'll work with GDB and not work outside, and that's the worst.
Yeah, so my question with that is I'm running to, when I hit Control D, when I'm running the function, I have to hit it twice for it to get to exit that function.
Okay.
But when I'm in GDB, I only have to do that once, and it exits fine.
That seems surprising to me, because that doesn't sound like a memory issue.
I actually have the same thing. I was curious about that.
Yeah. Throw some print statements in and figure out what it's doing after the first Control D when you're outside GDB, and see if you can find it from there. But yeah, that's a little weird, because if it's working in GDB, it doesn't sound like a array going out of bounds or something. So that's a little odd. But you can catch me at 12 and show me if you want. All right, other questions? All right, so let's talk about the lab. All right, so here's the goal of Lab 4. Lab 4, you're going to write something that basically generates Morse code using an LED. And when you run your program, you can type something like hello and hit enter. And your LED should blink out the dot and dash pattern for the letters that you typed. And so sort of the standard test for that is SOS. So SOS is 3 short flashes, 3 long and 3 short. So if you do that, there's the 3 short, there's the 3 long, that's the letter O, and then 3 short, that's the letter S. All right, so that's your goal, right? Make something that generates Morse code. So let's look at the assignment. So you're going to do this from C, okay, instead of doing this from a shell script. And let me shut this thing down. I'll leave it up. So you're going to do this from C. So let's go through the details. So interfacing the GPIO lines from C, the following steps. In the beginning of your program, you have to include wiring pi.h. Okay, number sign include, put it in angle brackets. We're going to stick to using GPIO4, which is pin 16. Pin 14 is ground. So I've just got an LED connected between 14 and 16, same as usual. One time in the beginning of your program, you have to call wiring pi setup. That initializes all the internal structures to do GPIO. And then one time in the beginning of your program, you have to call pin mode and set your pin to be an output port. So the 4 means GPIO4, and output is just a keyword. And then anytime you want to write a voltage level to that pin, you call digital write. Either write a high or a low to write 5 volts or 0 volts. And 4 again is the GPIO number. To compile your program, you need to put this -L wiring pi at the end of your GCC. And you may want to put -standard equals C99. You may have discovered that, but that lets you do things like define integers inside for loops and stuff. But you need this -L wiring pi, just like -LM to include the math library. This includes the library for doing standard I/O. And if you just try to run your program like this, it'll say you must be root. Okay, so you need to use the sudo command. Sudo and then the name of the executable. And it may or may not ask you for a password. If it asks you for a password, it's whatever password you set up for the Pi account. So it's usually username Pi, password Raspberry, or other way around. Okay, so those are all the details for compiling this thing, getting to the GPIO lines. Wiring is the same as we've been doing. Ground on pin 14, LED on pin 16, put in a 1K resistor. So it's a really simple circuit. All right, so 2 experiments. First experiment, blinking LED. Turn the LED on for half a second, turn it off for half a second, loop forever. Okay, that's your hello world. That makes sure that you can compile and make sure you're including the libraries, you're linking correctly, you're executing with sudo, you can get to the actual port, and you can do some timing. Okay, so lots of check boxes that get taken care of when you do experiment 1. Even though it looks like a really simple experiment, it's actually all the really hard initial steps. Experiment 2 is the Morse code generator. So read from standard in, person types something in, hits enter, blink the LED in the proper dot and dash pattern for each character that they type in. So simplifying assumptions, only worry about letters. Punctuation, spaces, digits, everything else, just ignore. Okay? So you read a character, if it's not a letter, ignore it. Read the next character. Don't wait, don't flash the LED, you don't have to print an error message, just ignore it silently. So if you say hello, space, there, exclamation mark, it should just do 5 letters for hello, 5 letters for there. Treat uppercase and lowercase letters the same, and I'm going to show you some code to take care of some of these things. For a dash, so basically each letter corresponds to a pattern of dots and dashes. So an S, for example, is 3 dots, an O is 3 dashes, an E is a single dot, a V is 3 dots followed by a dash, and so on. And there's a pattern associated with each of the 26 letters. And I'll give those to you in a file so you don't have to type them in yourself. So if you need to display the letter V, you need to blink the LED in a way that represents 3 dots followed by a dash. So here's the timing. And I need to update the assignment to make this clear because I missed one part of it. So turn the LED on for 0.1 seconds to represent a dot. And then wait for 0.4 seconds. Turn it on for 0.1 seconds to represent a dot. Wait for 0.4 seconds. Turn it on for 0.1 to represent a dot. Wait for 0.4. Turn it on for 0.4 to represent a dash. Okay, so this corresponds to dot, 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 dash. And between words, wait for a second. I don't care if you do that extra 0.4 or not there. We'll put in a nice 1 second wait between each letter, okay? And for each letter, If you want to indicate a dot, turn your LED on for a tenth of a second. If you want to indicate a dash, turn it on for 4/10 of a second. And wait 4/10 of a second between each of these dots or dashes. Does that make sense? All right, so I need to add the 0.4 between dots and dashes in here, but I'll put that in later on today. So a bunch of hints and guidelines here that will save you a lot of work and save you from asking me questions where I'll say, take a look at the lab assignment. So there's a command called uSleep that waits for a certain number of microseconds. So if you want to wait for a tenth of a second, call uSleep 100,000. If you want to wait for 4/10 of a second, call uSleep 400,000. And for experiment 1, you want to wait for half a second, call uSleep 500,000. Okay, it's millionths of a second, microseconds. To use the uSleep function, you need to include unistandard.h. And when you compile, you'll get compiler warnings. I don't know why, but just ignore them. Okay, if it's warning about undeclared function uSleep, just ignore it. Something's weird. Okay, I strongly suggest writing your code in a modular way. So your top level task is something like, oh, that's weird. Yeah. Anybody know how to change your rotation? And it's a keyboard keystroke. Well, we can just live sideways. That's fine. So here's a view of an algorithm, right? Read a line of text. For each character, if not a letter, just ignore. Otherwise, find a dot and dash pattern. And then for each dot or dash in here, blink the LED. And then wait 0.4 seconds. And at the end of this, wait 1 second. You don't have to do it like this. This is just one view of it, right? So read a line of text, go through character by character, or just read a character at a time if you like. If you like get car, right? But for each character, see if it's a letter. If it's not, ignore it. Otherwise, find out the pattern of dots and dashes, and then for each dot or dash in that pattern, turn on the LED for the appropriate amount of time, turn it off, wait 0.4 seconds. Do that for the entire dot dash pattern, and then just wait 1 second and go on. Okay, so that's basically what's described in here. No. Okay, so that's your basic algorithm. But this means you can modularize your code, right? You can write a function that basically takes a dot or a dash and blinks the LED the right amount of time. Well, first thing you do is write a function that turns your LED on, write a function that turns your LED off. And you don't have to be dealing with this digital write high and all that kind of stuff everywhere, right? Make an LED on, make an LED off, or make an LED function that takes a 1 or a 0 to say, should I turn it on or off? Whatever you like, right? And then make a function that displays a dot. So what does it do? Turn the LED on, wait 1/10 of a second, turn the LED off, wait 4/10 of a second. Make a routine that displays a dash. Turn the LED on, wait 4/10, turn it off, wait 4/10. And then make a function that takes a string of dots and dashes and displays that in Morse code. How does it do that? It just calls your dot or dash function. right? So for I equals 0, I less than string length I plus plus, if string bracket I is a dot, call my dot function, otherwise call my dash function. And then make a function that takes a letter and displays it in Morse code. How does it do that? Well, it takes the letter and somehow it figures out what the dot dash pattern is. And I'll show you how to do that in a second. And now your main program basically gets a character, checks to see if it's valid, and if it is, just calls your display function, right? So you can keep modularizing this thing into further and further pieces. All right, so how do we find the Morse code pattern? Well, here's a nice little definition of an array called patterns. It's got 26 entries in it, and each entry corresponds to the dot dash pattern for the next letter. So patterns bracket 0 is the dot dash pattern for an A, patterns bracket 1 is the dot dash pattern for a B, patterns bracket 25 is the dot dash pattern for a Z. So there's a file on the server under /temp called morse.txt. It's got all of this initialization for you. So if you don't like typing, right, just take that, grab all of that, go into your Pi, and just paste it in, right? And now in the beginning of my code, I've got my Morse code definitions with some extra spaces. Don't worry about that. All right, so take advantage of that if you want. So if you have this patterns array set up in your program, here's some code you can use to find the dot dash pattern corresponding to a letter. Take your letter. If it's not an alpha, just return, okay? Because it's not something that we're going to blink. Otherwise, call 2-upper. So C is the character we're trying to display. So set C equal to 2-upper C. So now it's an uppercase letter A through Z. So here I'm going to let you do some ASCII arithmetic. Subtract the ASCII code for A from your character. This will give you an integer index which runs from 0 through 25. And now if you say pattern bracket index, that will give you the dot dash pattern corresponding to letter C. Does that make sense? So if C is equal to the letter H, that'll have an ASCII code of 72, right? It's an alpha. You convert it to an uppercase H. It's got an ASCII code of 72. You subtract the code for A, which is 65. That gives you a 7, or an 8, 7. And now if you say pattern bracket 7, right, 0, 1, 2, 3, 4, 5, 6, 7, gives you this, which is the dot dash pattern for an H. And you can either work directly with that, or you can string copy it. And then go to town from there. Right, so if C is not an alpha, return. Otherwise, convert it to an uppercase. Convert it to an integer from 0 to 25. So here's one way to do this. String copy into temp, patterns bracket I. And now temp is a string containing dots and dashes. Right, so now for I equals 0 to length of temp minus 1, temp bracket I is a dot or a dash. All right, so you can say if it's a dot, display a dot, else display a dash, and so on. Got the idea? Everybody think they can do this? What?
What did you say? A is blank?
A, where are we?
The top?
Display.
Oh.
All right, so there's your code for pulling in, getting an index, string copy it to a temp. Okay, and you're good to go. All right, so sign off. 2 experiments. First experiment, LED blinks on and off, half-second interval. Okay, that's your hello world. Witness that with someone, get them to sign off. Experiment 2, if you type SOS and hit enter, it should blink 3 fast blinks, 3 slow blinks, 3 fast blinks. Okay, so demonstrate that. And then if you type something like your name or hello or this is fun, it should do something that looks like believable Morse code. Okay, I trust you're going to actually do this and not just make it blink random patterns. But it shouldn't just blink the same for SOS no matter what you type in either. So, so type in your name or something and it should blink. All right, so, so there's no lab 5. Okay, this lab is double, so it's 40 points. You've got 3 weeks to do it instead of 2. It's not necessarily 50% harder or twice as hard as the other labs, right? But I don't want to have you doing labs and SLPs and ODPs and studying for exams and PA5 all at the end of the quarter, right? So we're probably done with ODPs for this course. This will be your last lab for this course. So you'll be able to concentrate on PA5, this lab, and your SLP, and then exams, and we're done. So don't leave it for the last minute, but it shouldn't be too bad to do. So I will not be here on Friday, so you can use class time Friday to work in the collaboratorium either on this lab or on PA5. Okay, PA5 is going to be a group project, and we'll go through it tomorrow in detail. So, so you can make use of the class time either way. So any questions about this? Gotta figure out how to unrotate my lab 4. There we go. All right. I made myself a fresh version of my Raspberry Pi the other day, and everything works as far as compiling and running, so it should work on yours, but if it doesn't, let me know. But again, don't make that discovery the day before it's due, because it takes time to fix these things. All right, other questions, concerns? So I don't think we talked about the source command in here. Is that true? I have it listed that we didn't get to that. Okay, so let me talk about some odds and ends here. So we already talked about this, right? If I set x equal to 123 and I go into a new bash shell and I echo x, its value isn't set, right? And if I've got x equal to 123, and I run a script that tries to echo the value of x, x doesn't have a value, right? And so the solution to this was to say export x, and I believe we talked about that. So now if I say do this, x has a value, and if I start a new shell, x still has a value. Right, so export lets me set a value to a variable here, and when I create a new shell, that value will be exported to that shell. Okay, but here's a different problem. So I've got this file called setx. It sets a value of new var to be 999. And if I run setx, and I try to look at the value of new var, it doesn't have a value of 999. And the problem here is basically, here's my main bash shell. I'm creating a new shell when I run setx. And inside here, I give a value to this new variable. But there's no way that that value is going to get pushed back to my original shell. Right? It's really no different from saying bash and setting a value to a variable in here and then expecting that somehow that value is going to come back to this shell. Well, that doesn't happen. Okay, so we've got this script and we'd like to set the value of new var to 999, but if we just say name of the script, it executes it in a new shell. So there's another command we can use called source. And if we say source followed by the name of a file, it basically reads the lines in that file and executes them in our current shell. So it will act as if I type $! bin bash, and then it'll act as if I type new var equals 999. And now if I look at the value of new var, it's been given a value. So if you have stuff happening in a script and you want that stuff to happen in your current shell, you may want to use source instead of just executing it. And this is useful when you're setting up your bash RC, because if I just run bash RC, everything it does happens in a different shell. But if I source my bash RC, it actually executes it in my current context. So that can be useful. All right, so I want to pick up, we got 10 minutes here. I want to pick up some odds and ends related to bash. And then tomorrow I want to talk about how we make GUIs from bash, and I want to talk about PA5. And since I'm not here Friday, I want to get through PA5 before then so that you have the weekend to start working on it. So that'll be mostly what we do tomorrow is GUIs and PA5, and they're related. But let's pick up some odds and ends for the next 10 minutes. So there's a command called type. If you say type fact.c, it tells me fact.c is a file sitting in my current directory, /fact.c. If I say type gcc, it tells me gcc is user bin gcc. If I say type pwd, it says pwd is a shell built in. Okay, it's not a program that gets executed somewhere in one of these directories in my path. It's a built-in function inside bash. Echo is also a built-in. But there's also an echo under /bin. There's a program named echo, but in bash, if I say echo, it actually executes a command built into bash. It doesn't actually use /bin/echo. Type is also a built-in command. Basically, it tells you, is this a file sitting somewhere in a directory, or is it a built-in command, or is it something that's not found? A built-in command. Like pwd is built in.
What if you do like where is type?
I think it'll say not found. Right, so it's really something that's in the shell itself. Right, if it's a shell keyword. So it can help with sort of figuring out what's what. All right, so the read command, right, so this -n thing, again, you don't have to use this unless you're trying to automatically return after a certain number of keys have been pressed. So if I just type a 1 and hit enter, x is equal to 1. But if I type 1, 2, 4, as soon as I hit that third key, it immediately comes back. It doesn't give me a chance to type in anything more, and now x is just equal to those first three keys that I hit. So if I type A, B, C, as soon as I hit the C, it comes back right away. So we don't usually want to do that. We used it in high-low because we didn't want to have to type H enter, L enter, right? But in general, if you just want to read until the person hits enter, you don't do that. You just say read X, and they can type as much as they want, and nothing happens until they hit enter, and then everything they type goes into that variable. Okay, there's also read-P. And read-P displays on your screen a prompt, and then it does the usual read X. So you can type in whatever you want, and that becomes the value of X. But read-P is different from echoing and then reading. And the difference is read-P is not actually displaying this prompt on standard out. So if I do read-P, enter something, and I redirect this into a file, I still see enter something on my screen. Even though I said standard out should go into this file called out, it's still displaying this. So there's actually two output streams available in Bash. There's standard out and there's standard error. Standard error does not get redirected when you say greater than, and when you say read with a prompt, it actually displays that message on standard error. So if you're just doing this for yourself and you know that you're working with an interactive session and you want to display something on the keyboard, use read-P. But if you're not sure, go ahead and do an echo and then a read. Right? And this is why read-P messed up some people's ODPs way back in the beginning. All right. Another option is read-S. So S is the secret option. So you type whatever you want and you don't see it on the display, but it still goes into your variable. So that can be nice if you're prompting for a password or something.
So basically it just doesn't display with typing out?
Exactly, yeah, it suppresses the automatic echo. All right, so set-O, there's various options we can turn on and off in Bash, and they're specified with this set-O. So one option is ignore EOF. Another option is no clobber. And let's see what those do. So set-O, ignore EOF. So if I'm sitting here at a prompt and I hit Control-D, instead of exiting, it'll say you got to use exit to leave. Normally Control-D signifies end of file, and if I'm just sitting here in a shell and I hit Control-D, it closes out my shell, which I like because that's quicker to type than exit. But if that gets you in trouble, if you hit Control-D and it keeps exiting your shell, you can turn on ignore EOF, and then Control-D just says if you want to leave, say exit.
So what that does,
It stops Control-D from exiting the shell.
okay.
I don't know what happened just there. I think enough of them will get you out. Maybe 10. Yeah. And you can specify how many it takes to get out. All right, so set-O no clobber. So here I've got some stuff. So I have a file named fact, right, which generates 10 factorial. If I do something like date redirect fact, right, This executes date command, puts the output into a file called fact, and now if I look at this file fact, it's got the date in it. While a fact was a really important program to me, I just clobbered it, right, by redirecting file into it. So you can set -o no clobber. And now if I have a file like my main file here, and I try to overwrite it by redirecting output, it'll say that file already exists. I'm not going to let you overwrite it. So it saves you from accidentally stepping on files that exist, which I find annoying, but some people find really useful. So it's all about setting it up to whatever works for you. And I don't know if I can force it to do that. Nope. All right, so that's another option. Another option is VI. So if I come back to a previous line, right, I can move forward and backward with my arrow keys. I can do a Control-A to go to the beginning. I can do a Control-E to go to the end. I can backspace. And there's a few other things I can do. If you say set -o VI, you now have the ability to use VI commands to modify this previous command. So I can use B to go back by an entire word. I can use CW to change a word. I can use tildes to convert from lowercase to uppercase, and so on and so forth. Maybe useful, maybe annoying. Okay, when I first figured this out, I thought it was the greatest thing in the world. And I started using it, and it drove me crazy. Because I kept forgetting that I was in VI. And if you forget you're in VI, and you are, everything gets weird, right? Because everything gets interpreted as a command. But it's another option, so set -o VI. We're almost out of time. Okay, let me just mention the command touch. If you say touch and you put in a file name, it basically creates an empty file with that name. If you say touch and you have a file that already exists, it basically updates the modification time of that file. And that's mostly used in make files if you want to force your make file to recompile a program. If you touch a .c file, it'll think that you've modified it, right? Because it'll set the modification date to be right now. And then if you say make, it'll go ahead and recompile and so on. So touch is useful, and it's a nice way to just make an empty file instead of VIing and saving an empty file.
Dash big O, capital no clobber.
Say what?
Or C.
Nothing. That was a Control-C. I aborted that command. I went up and came back here, and then I hit a Control-C, so it looks weird. All right, so let me just mention umask is a command. When you create a file, like haha, it comes with a certain default protection. Usually the default is 664, read-write for the owner in the group, read-only for the world. You can change where that default is. Okay, the command for doing that is umask. And either look at the man page or experiment with it or ask me about it if you want to know how to use it. But there is a way to change that default. It's the command umask. It's a built-in in bash. But we're out of time here, so I will leave it at that. So we'll talk about PA5 and we'll talk about Zenity, which is how we create GUIs tomorrow.